Yeah, let's continue to develop a chromatography theory. Okay, now consider the concept of plate height, which is the measure of column efficiency. Okay, um, you see, the diffusive band spread as it travels through column. Yeah, we here um, we already learned that as a solute is moving along this column, at first it is concentrated in a very small region, but as it goes down and it spreads out because of mostly the diffusion. Okay, so here we define Ux is a linear flow rate and UV is volume flow rate. Okay, and sigma square is 2dt. D is diffusion coefficient and T is time. Okay, time is what? Distance divided by flow rate, and it is given by this one. Okay, here 2d x divided by ux, and now 2d divided by ux, which is we denote by large h, and we call it plate height. Okay, but actually, what's the concept of plate height? Okay, this one I made this figure by myself. Isn't it wonderful? Okay, here is the chromatographic column. Yeah, this blue one. This is open tubular column, right? And then here this yellow one is the stationary phase. Okay, this is chromatographic column. Yeah. Of course, you can fill this column compactly with stationary phase, but here I wanted to show that the stationary phase and the mobile phase, and the light blue, this color is the mobile phase. Now mobile cage carries this solute, red color, down this column, right? And then uh, this solute now there is equilibration between equilibration of solutes between this stationary and mobile phases. Okay. Well, what is the plate height? So the in an early development of the theory, people thought that they divide this entire column, okay, whose length is L, into several, the many small plate. Okay, this one is each plate. Yeah, this part is each plate, and then they assume that this solute now become in equilibration between the stationary phase and mobile phase. Okay, but actually, this equilibration is a dynamic what process, but theoretically, okay, we can think that the solute make equilibration in this plate and then move down to another plate, and here again solutes become in equilibration between this stationary and mobile phase, and then like that. Okay, now you understand it, right? But actually this is not such a discrete process, but it's a continuous process, but theoretically we can think of that. Okay, in each plate here solute uh, what there is a equilibration of solute between mobile and stationary phases, okay, within the plate, right? And here this plate height h, and since the total length of the column is L, and if we divide this L by H, that's the number of this N is plate numbers. Okay, so when the plate number is large, that means there is a many equilibration absolute until it comes out of this column here. Okay, yeah, that's the concept. Mm. Okay, now go back to this slide. So if we rearrange this equation, then the plate height h equals sigma squared. Yes, this is standard deviation divided by x. You see, x is what? X is here the distance. Okay, so height equivalent to theoretical plate. Okay, so the here the n is theoretical plate number, right? Concept of this height column length required for one equilibration absolute between mobile phase and stationary phase. Okay, as I just explained, the smaller h, the narrower the bandwidth, which means the better separation. Okay, so it is important to make this plate height as small as possible. Okay, for the better separation. This the plate height h for gas chromatography is around 0.1 to 1 millimeter. Okay, but for the liquid chromatography, the plate height is much smaller. It's smaller than 1 micrometer. Okay, so for the gas chromatography, sometimes you need very long column, and for the capillary column, sometimes you need to have maybe 100 meters column. Okay, but for the liquid chromatography, column length is not very long, maybe several tens of centimeters. Okay, that's enough because the plate height is quite small. Okay, so now let's summarize the theory here. The number of plates n equals L divided by H, and uh, when we recall x equals L and sigma equals W, this is the bandwidth of the chromatogram divided by 4. Then we hook up this one here, yeah, and so we get this equation. Yeah? Number of plates equals L squared divided by sigma squared. Right? And here 16 times L squared divided by W squared. Okay? And then we can further uh, calculate for the number of plates on column n equals 16 times TR squared divided by W squared, which equals TR squared divided by sigma squared. Okay, now TR and W here, yeah, are expressed in time. Okay, not in length, because actual the chromatogram expresses in terms of time. Okay, so we can equivalently you can consider they are all in times. Okay, so finally we get this equation: the number of plates on column n equals you recall the W1 half equals 2.35 sigma. Okay, and then we get this equation n equals 5.55 times TR squared divided by W1 half squared. Alright, here is an example to measuring of measuring plates. A solute with a retention time of 407 seconds has a width at the base of 13.0 second on a column 12.2 meter long. Find the number of plates and plate height. We now know the total column length, and if we know the number of plates, then we can calculate plate height. If we know the plate height, and then we can calculate the number of plates. Now we can use this one, yeah, because here is the retention time is given. All right, and this W is the base width in terms of second time. Okay, now using this one, we simply substitute necessary numbers here, and then we get number of plates is 1.57 times 10 to 4. All right, now this is a theoretical number, right? Invisible number actually, yeah. And h is what? L over n is 0.78 millimeter. Okay, yeah, very easy actually. And now, what if the chromatogram is not symmetrical? Okay, this is asymmetric peak. Okay, but so far we only considered the symmetric peak, the Gaussian shape uh, curve. But actually, we meet this kind of peak shape very quite often. Okay, and then we need a theory. But in this book, the author didn't derive the theory for this one, right? And for this kind of asymmetric peak, your textbook says n uh, is approximated by this equation, right? This is much complicated, okay? But we simply accept this equation. How do we do that? Now you take measurement of this height, right, and divide by into 10, yeah, and then you measure from the bottom the 1/10 of the this length, and then you here you draw the line here, and then here at the 1/10 of length. Then the right hand side is a, the distance is a, yeah, in terms of time, and left hand side is b. Okay, so n equals the constant 41.7 multiplied by tr. Tr is the retention time at the peak height, divided by w 0.1. Okay, this is the length at 0.1, and squared, and divided by a divided by b plus 1.25. Okay, here w 0.1 is the width, which is the a plus b at 1/10 height. Okay? Yeah. Well, you don't have to memorize this complicated equation, all right? And for your reference, and this is a general case. For the symmetric case, a and b is the same, okay? And then you will end up having this kind of this equation, okay? That's left for your exercise, all right? Now let's consider the factors affecting resolution. Okay? Yeah, this is very interesting. Resolution is what? Like mass spectrometry. Let's see. We've already considered the resolution here, yeah? You see? Yeah, here. Resolution was given by this equation, okay? But now let's consider the factors affecting resolution. Now, resolution can be expressed in different way, okay? It is a square root of n divided by 4 multiplied by gamma minus 1. Okay, here gamma is a new parameter. It is called unadjusted relative attention. Okay, unadjusted one. And this one gamma is the ratio of UA divided by UB. Yeah, U is the linear velocity, which equals TB divided by TA. T is retention time. Okay, gamma is defined by this way, yeah? And resolution is defined by this way. Okay, so what is important, yeah, in this equation is that resolution. You have to have the better resolution. That means this number must be as high as possible. Okay, but now n is what? N is number of plates. Okay, and very unfortunately, resolution is proportional to square root of n. Okay, it is like that. Uh, when you learned spectrophotometry, yeah, to increase the signal to noise ratio, right? That increases with the number of measurements squared. Ah, no, not squared. The square root of a number of measurements. Okay, so to increase, 10 times signal to noise ratio, you must at least take 100 measurements. Okay, if you want to increase 5 times, and then at least 25 measurements are necessary. Okay, here is concept is the same. Resolution is proportional to the square root of n. N is number of plates. Okay, here is a good example, right? Separation of L-phenylalanine and L-phenylalanine T5. Okay, this is the structure of phenylalanine. Okay, and T5 is what? There are five the hydrogen atom one on this benzene ring, 1 2 3 4 5, and then they are all substituted by deuterium. Okay, D 1 2 3 4 5, and this one is a little bit heavier than this one, original L-phenylalanine. And since there is a small mass difference, okay, so theoretically it is possible to separate these two, okay, but it is not very simple. Okay? Let's assume you have these two compounds in a same solution, yeah, with a same concentration, okay, and then you run the chromatography, okay, and this n value is what? Is the number of runs, and theoretically, yeah, from this resolution equation, to separate, to have a better separation of these two species, yeah, you need to have a very large number, okay. To have a very large, the plate number, you need very long column, yeah. But practically, it may not be possible. How do you do that? Yeah, there is one good way, which is that you run first, okay, first run, and then you collect all the separated material, and then you run again, okay, run again, okay, and then that is equivalent to increase the column length. Okay, here at first run, there is a little separation, okay, but it is not enough, and then you run again, okay, after collecting the the element, and then you get here this is second run, and then the response becomes smaller, but peak width becomes a little bit fatter, because there are the constant amounts of these two species. Yeah, still for the second run, separation is still not good, and then you run third time, and it becomes better and better. Okay, this one, the small peak is the deuterated phenylalanine, and this one is one the phenylalanine. Okay, you run, several times, maybe 10 times. Yeah, after run 10 times, and then have you begin to have better separation. And then after 15 times, okay, you have a better separation. Yeah? And this one, this plot is the resolution squared, yeah, versus number of passes. Okay, here if you scale this one, and then you this one is square root, is removed. Yeah, and if you repeat chromatographic running, and then resolution becomes better and better and better. Okay, and at 15 runs is resolution squared is about 3.5. Yeah, and resolution is what, less than maybe 2, but more than 1.5, maybe 1.8 or something like that. So that's enough. Okay, this is a very practical technique. All right. Yeah, here's a good example. Plates needed for desired resolution. Two solutes have an unadjusted relative retention of gamma of 1.06. Okay, this gamma, this one, this you know, the gamma value is so small. Okay, so it is not easy to separate the two solutes. The question is, how many plates are required to give a resolution of 1.5? Yeah? Okay. So here, again, 1.5 resolution is enough. So resolution 1.5 squared is 2.5 here. And in this graph, 2.5 is about 10. 10 repeated passes is enough in this case, okay? But here, the question is to get the resolution of 1.5 and 3.0, how many plates are needed. Okay? If the plate height is 0.5 millimeter in gas chromatography, how long must the column be for a resolution of 1.5? Okay, so now we can use this equation. Okay, you memorize this equation. 1.5. Let's consider 1.5 resolution first. Yeah? And then, since we are going to calculate n equals, now we solve this one, and then n equals 1.0 times 10 to 4 plates, 10,000 plates. Okay, to double the resolution to 3.0, we don't need to calculate this again. Why? Because the resolution is proportional to the square root of n. Now resolution from 1.5 to 3.0 and 2 times improved. So number of plates must be 4 times, okay, larger. So actually, you know, 4 times the larger, which means the column here, column, the plate number is 4.0 times 10 to 4 plates. Okay, you understand? You don't need to calculate this kind of calculation again. For resolution 1.5, another question is the column length. Column length. So since the plate height is given, which is 0.5 millimeters, and now you multiply the number of plates by this each plate height, okay, and then we get 5-meter column. Okay, so you need to have 5-meter capillary column, okay, for the resolution of 1.5. Okay, easy. So this table summarizes the chromatography equations. So far, we developed rather in detail, right? And then we introduced many parameters, and many also we set up the many equations here. It is not wise to memorize all of this, okay? But rather you solve the problems at the back. Yeah, you try to solve the problems, and in the meantime, you will get the concept of chromatography, okay, and concept of plate height, plate number, okay, and resolution, and something like that. Okay, yeah. This is just a simple summary of chromatography equations. Wow, this is classical case. Okay. Okay, now let's temporarily stop here.